Lecture 2 is going to start talking about statistical learning. So we're first going to introduce the framework, and then we're going to introduce our first statistical learning procedure or approach, that is linear regression. So the title of this lecture is Linear Regression. The first thing we want to do is talk about learning problems. So broadly, there are two types of learning problems. One, supervised problems, and two, unsupervised problems. We're going to talk about both of these over the course of this course, and we're going to first start by talking about supervised problems. So this is going to take up roughly kind of the first half of the course. And sometime around after the midterm, we'll start talking about unsupervised approaches. So supervised learning is basically the approach where we have some training data, what are called training examples, and we are going to learn from them. And we'll talk about what exactly learning means, but we have some quote training examples, and we're going to learn from them. So this is basically a prediction problem. Where I want to predict some y from some x. And we're going to have examples of both y and x. So in the supervised context, we have examples of y and x. And we're going to use those examples to learn the relationship between these. So regression has, let me back up, supervised learning has two major, or indeed two at all, two subproblems. Or flavors. Let's call them flavors. And the two flavors of supervised learning are, one, a regression problem. And regression here, I'm going to put scare quotes around it. So regression is kind of a loaded term or an overloaded term in learning literature, in machine learning, statistical learning literature. It both refers to a particular technique, say linear regression, but more broadly, regression, or regression-like problem, refers to predicting a quote, continuous outcome. And this would formalize where the thing that we are predicting is literally going to be a continuous random variable. So examples of a supervised regression problem would be we want to predict stock price from economic indicators. Maybe not so good for predicting the price of GameStop. Another example of a supervised regression problem. Maybe we want to predict adult height from childhood diet. If you have a good diet, we would expect you to be taller, generally speaking. The other flavor of a supervised problem is what's called a classification problem. So regression, not surprisingly, is going to be an example of a regression technique, or so that's kind of a weird sentence to say, but regression in our context broadly refers to just predicting where our y here is going to be a continuous outcome. When it's not continuous, we call that classification. So this is where we're predicting a categorical outcome. And statistical learning literature, we're going to model these as discrete random variables. So some examples of a classification supervised learning problem. One that you will get paid to work on, or could get paid to work on, and that's of interest to all companies that extend credit, would be: will an individual default, i.e. not pay, on a loan given maybe credit score? Can we predict if an individual is going to default on a loan given their credit score? So here my outcome is two options. And so I can always encode this basically as a binary random variable, or binary variable. 0 means maybe they don't default, and 1 being that they will default. So this is of interest to banks, to car companies. They want to know, are you going to default on your loan if we give you a loan for this certain amount? And so there's a lot of statisticians being paid money to build models to predict this. And there are various parameters and variables they're allowed to use and not allowed to use. But this is it's a real problem, and I have colleagues who've worked on that. So another example, maybe from healthcare, would be to predict disease status from blood work. Again, my outcome, so for example, y that I want to predict, is again, you could encode as a binary random variable. 0, maybe no disease, and 1 being they have whatever the disease is that you're looking at. So this is something, this kind of pathology is something that people are working pretty hard, for example, in radiology, to, not blood chemistry, but for images, to get some artificial intelligence working as well as humans. So both these examples so far of supervised classification problems, we'd have binary outcomes. Another example we could look at would be, let's say we can predict race from genomic data. So here is what is called a multi-class problem, where we have more than 2 classes. So here my outcome is going to be a whole bunch of different races. And kind of alternatively, these problems where we're predicting one of two outcomes are called binary. Binary problems. So binary problems are the simplest, and there's a lot of really interesting binary problems, disease or not, default or not. But there are also some, and it's much harder, there are some very interesting multi-class problems where we have more than two possible outcomes. So we won't get to classification for a little bit, but when we do, maybe a lecture or two, we'll first start with the binary ones. And oftentimes you can build up what called classifiers or algorithms or models to solve these classification problems. From the binary problem, you can build it up to the multi-class problem. So this is still only half the deal, right? Because supervised learning, let's say we have, I guess I said one, but whatever. We have two types of these problems, right? We have the supervised problems, and then we have the unsupervised problems. So supervised problems are basically where I want to predict a y. Maybe I want to, I want to predict stock price, predict adult height. I want to predict default status, disease status. I want to predict race, and I'm going to do that off some data that we've talked about. And it's supervised in the sense that I have some examples of what that relationship between y and x looks like. The whole point is to learn to generate some algorithm or generate a model that will ultimately predict y, some new examples of y, given new examples of x we haven't seen. But it's supervised in the sense that we're telling it in advance, here are some examples of, for example, the first problem, here are some examples of economic indicators and the corresponding stock price. And hopefully we can learn what the relationship is. That's basically the whole course, or half the course. The alternative, so we'll call it learning problem type 2, is unsupervised problems. And we won't quite get to these techniques until kind of the second half of the course, but contrasting with supervised, an unsupervised problem is basically anything that's not a supervised problem. Basically, we don't have, quote, our training data. So we don't have examples of y's and x pairs. All we want to do in an unsupervised problem is we want to learn or summarize interesting, important trends in the data. It seems a bit vague, and it can be a bit vague at some points, but there's not as much of a well-defined problem. There is no specific quantity we are predicting. So this will make a lot more sense after we've done a bunch of supervised stuff and we talk about these unsupervised. But unsupervised techniques are just trying to learn some patterns in the data. And trying to summarize the important patterns. We don't know a priori exactly what we want to predict. So that's kind of an overview of the course. We're going to basically go through these in that order. So we're going to go through these different learning problems and learn different examples and talk about how they're all related to each other. We'll start with supervised learning. We'll start with some regression problems. Indeed, today we'll talk about linear regression. And then we'll talk about classification problems, classification algorithms, and unsupervised problems later in the course. And so this course can be a bit topics-y, in that, we have there are many different examples of, quote, algorithms for solving these different supervised and unsupervised problems. Part of the course is going to be to learn the kind of pantheon of different algorithms that are out there. But more importantly than that, part of the course is going to be to learn about the relationships between them, which will tell you something about their relative strengths and weaknesses, and kind of more broadly learn the basic theory of this stuff, because you can't teach a course that covers everything out there. And what I'm going to try and do in this course is teach the general principles so that you can then go out and absorb a new method, a new approach, and understand kind of how it fits in to the existing approaches, how it might work, and what some pitfalls of it. Sight unseen, you'll have some kind of general framework on which to pin new things that you can learn. That being said, let's not delay any further. Let's start talking about supervised regression problems. First, let's just talk about the general setup for supervised problems. And so a supervised problem has a couple important parts. We have some variable y that I typically use in this course. And this y is called different names. I'll often call it an outcome. It's the predicted variable. This is the thing we want to predict. It is sometimes called the dependent variable. It's the thing we want to predict. And we're going to predict y. Let me write that. We're going to at least try to predict y using other variables. And I'll denote them x1, and we'll say that we have some p of them. So here, p is going to be the number of variables. And these other variables have many different names depending on what what kind of group you run with. These might be called the predictors. They might be called features. They might be called covariates. They might be called the independent variables. But basically, they're the things used to predict y. So we have y, the thing we want to predict, and the x's, the things we want to predict. Or we have y, the things we want to the thing we want to predict, and the x's, which is together constitute the things used to predict y. So what do we mean by predict? What we mean is that we want to come up with a function f, and let me just say, we want to come up with a function so that when I plug my x's into this function, they are going to approximately give me y. The closer, the better. So oftentimes we will call the predicted among statisticians, we will call the prediction, sorry, I should write this on the other side. We will call the predicted y hat. And the whole goal of this course or the goal of statistical learning approaches is to, one, talk about, let's move this over, how do we construct F, and two, how do we determine if F is good. So we want to come up with a function, and I probably should call F hat. Let's rename our function. Instead of F, let's call it F hat. We want to come up with a function F hat so that our y's are going to be basically well predicted by F hat of the x's. We can call that prediction y hat. The goal of this course is going to be twofold. We want to talk both about methods, that is how to construct F hat, and we want to talk about evaluation. That is, how do we determine if this F hat that we've arrived at through our methods is good? So the way supervised problems work is that we are going to, let me just say this, we will use training data to construct F hat. So we're going to have some examples of pairs of x's and y's, and we're going to use that, quote, training data to construct our estimate F hat. So we've avoided it this far. Let's talk about some math. So let's just call this statistical learning. So the basic setup of statistical learning is we assume we have, let's say, some training data, and my training data is going to be pairs of y's and x's, and we're going to assume that we have some capital N of them. So maybe I should write it like this. We assume we have some training data, yn, xn, where little n goes from 1 to capital N. So here, capital N is the training data size, and little n is just my index. Our training data consists of pairs, yn, which is in some set, let's just call it S, and xn's, which are basically vectors of our covariance. So they're going to be in some p-dimensional space, right? What we said is that we have p covariates, x1 to xp. And so our xn's are numbers, and rp. So for example, xn is x n, oh, how do I want to say this? x1, which do I want first? I want to have, yeah, xn1, xn2 dot 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 xn p. So for each of my x sub n's, this is a vector in Rp of components. So these are basically the measured variables, covariates for nth observation. And my set S here is the continuum for classification problems. And for regression problems. And it is some set of classes, let's call it C capital K, for classification. So the basic setup is we have some what we're going to call training data. Training data is just a series of pairs of the things we want to predict and the predictors, the covariates. The YNs are for regression problems, they're just going to be some real number. For classification problems, they're one member of some discrete set. And here we're going to say that we have some capital K number of classes. And the XNs, the covariates, are measurements in some p-dimensional space. And for now, we're going to assume that through numeric, we can talk about non-numeric data, probably next lecture. And statistical learning approaches. So this is kind of a setup that you would get in a computer science course. You would get up to this point, you would have a very, very similar setup. If we want to make this a statistical learning, let's say for statistical learning, that's supposed to read learning. Let's rewrite that. We think of the training data this collection of YNs and XNs, this collection of n of these things, as having some maybe complicated joint distribution. So what really, statistical learning is basically machine learning done by statisticians. Statistical learning, the way statisticians think, they think of what's called a model. The data, they assume there's some probabilistic model. Let me write that down. Can I spell probabilistic? Probabilist. Hopefully that's how you spell probabilistic. What makes a kind of mindset of a statistical learning course or approach is that we think of the training data not as just being numbers, but as actually being observations from some maybe complicated joint distribution, that the data has some underlying distribution, and that basically we're trying to solve a statistical inference problem. So as I said above, the goal of a statistical learning approach is to construct an estimator f hat. So we want to construct some f hat. And so to do this, what we're going to do, if we're statisticians, is we're going to exploit this probabilistic model and let the model tell us what f hat should be. So what we'll do is we will, what did I write? We want to construct some f hat. To do this, we first construct a measure of, quote, wrongness, right? F hat is supposed to approximate y. So that when I plug my covariates into f hat, it's approximately supposed to give me back y. And so what is that measure of approximately giving me back? And this measure of wrongness is called a loss function. And typically a loss function is denoted L. And it's going to be a function from RP to R, so that if, you know what, it's not going to be from RP, it's going to be from my space of functions. So here I'm going to use the script f to be my space of possible f hats. Okay, so we want to find a good f hat. There's some space of possible functions out there, and we're going to create a loss function L that's going to take one of these possible f hats and spit us back a number, so that if I give my loss function some potential f hat, let's just call it f, then L of f is going to be some number that tells me how good a job that f does. So we want to find some good f hat to do this. What we're going to do is we're basically going to come up with a function that tells us, among all possible functions in my space, capital F or script f here, or for each of these, how good does that do at reconstructing y from x? Right? Basically, how close is f hat of, or f of these x's to y? So let me say that, i.e., how close is f hat, or in this case, we're just calling it f. Oh no, I lost my f's. How close is f of my covariates to what I want to predict? And we'll talk about exactly how this, we'll see one of those examples today. Once we, at this point, have all of these components, ideally what we would do is we would let f hat, our predicted, kind of our positive function that we're going to use, the algorithm, the learning algorithm to spit back, would be basically the minimizer of over all possible functions of the expected loss. So this quantity here is called the risk. So we have a setup where we have some training data. It has some underlying probabilistic model. We're assuming there's some relationship between the x's and the y's and we're assuming it in some probabilistic way. And what we want to do is find an f hat so that we can predict the y's from the x's. The way we're going to do that is we're going to come up with this kind of the measure of wrongness, which is called a loss function. It's going to take a potential f, and it's going to tell me how good of a job does f of these x's do at reconstructing y. And ideally what we do is we would minimize, we would let f hat be the function f over chosen from any of our possible functions in our space that minimizes the risk, that minimizes the expected loss, so that on average this f hat would do the best of any possible function in our functional space. Unfortunately, we don't know, we often don't know the joint distribution of the training data exactly. So instead, we minimize an empirical we minimize an empirical version of the above starred equation here. So instead, since we don't actually know how to necessarily calculate this expected, all we know about, so we assume there's some underlying probabilistic model relating the y's and the x's. If we knew what that model was, we wouldn't have to do the machine learning approach because we know what the model is. We don't know what the model is. All we have is our training data. All right. Well, we'll talk about that. All right. So let me just note that we only have training data. We don't know what the actual model is. If we knew the model, we wouldn't have to solve the problem in the first place. We don't know what the model is. We have some training data. So instead, what we're going to do is, since we can't calculate this expectation because we don't actually know what the probabilistic model is, instead, we're going to say, I'm just going to minimize over an empirical version of this, i.e., I'm just going to minimize the average loss over my training data. And so this is called empirical. Let me first say this is called risk minimization. And we don't actually know how to calculate this expectation, and so instead we are basically going to do what's called empirical risk minimization, where it's because we can't calculate that expectation, we don't really know what the probability distribution is, we're going to replace the expectation with an average there. So this is a little bit abstract at this point. Let's talk about a concrete example. And our first concrete example is going to be linear regression. So this is obviously solving a regression technique. Indeed, talking about these problems, they're called regression, supervised problems, you can think of as regression-like supervised problems. So linear regression is the first thing we're going to talk about. We're going to talk about it because it's kind of a super classic method. So it's really well studied. And you can get, there are whole books on regression. Secondly, we're going to talk about it first because it's really simple. And this is an accolade as far as I'm concerned, right? This is a good thing. Simple is good. Complicated, if you need a complicated algorithm to solve a complicated problem, not great. If you can solve it with a simple algorithm, that's great. The third reason we're going to study regression is that it can be really powerful. It seems like a kind of dinky first technique. Sometimes regression is the best thing to do, and so it can be a really incredibly powerful technique. And so if you've done regression, you've done machine learning, it's the first method we learn, and it can be a really powerful method, and so don't underestimate how good regression is. Lastly, as far as this course goes, regression is the basis for many other methods that we're going to learn throughout this course. And so it's important to have as the first method because tons of other things out there in the literature are just fancier versions of this. So regression, so we talked about this whole framework for statistical learning, and regression is linear regression is a regression technique. And again, the whole goal is that we want to learn f hat, right? And in my statistical learning approach, right, we said that we're going to assume we have some training data, x's in RP, y's in this case in R, and we're going to assume there's some underlying probabilistic model. And the model that regression is going to posit is the following. We'll de-emphasize at this point a little bit the probabilistic point, but it posits a model where y, we should say regression posits, I can spell posits, regression assumes, I can spell assume, regression assumes that y, which is f of my x's, is linearly related to my x's. So it's some beta naught plus some coefficients times my x's, and then I sum them up. So this is a linear relationship. Between the y and the x's. So regression assumes, as the name implies, that there's a linear relationship between the y's and the x's, which takes this form: beta naught, the betas being some coefficients. But there's some intercept, and then there's some slope terms associated with each of the x's. If we let x tilde be the vector that in its first component has a 1, and then in the subsequent components has my x's, so this is going to be a vector in R, not P, but RP plus 1. And if we let beta be my vector of coefficients, beta 1 to beta p, so this again is a vector in RP plus 1, then we can simply write this as y is x tilde transpose beta. So that's a cute way. It turns out that it's just an inner product. So linear here. So we say that regression is linear because f hat or f is linear in the betas. So let me back up a moment here. Let's just notationally make the following distinction. We want f hat. So f hat is going to be what we're going to, is going to be our estimate. So we'll use this, we'll try to use this notation for the rest of the course. F hat is going to be our estimate. And f is going to be, this is the true underlying model. And in this case, I'm kind of suppressing the probabilistic standpoint of it, but you could assume that there was, some epsilon, you could add on plus some epsilon that's normal. It's a little bit more of a statistical inference thing. We'll de-emphasize it for now. But so f hat is our estimate. There's some true underlying f. We're going to assume that there's some true underlying model, and f is, in this case, going to be our true underlying model. And so the betas are the true betas associated with the true functional relationship f. And in this case, the true functional relationship is just linear. And so this true functional relationship can be written as this inner product of x transpose beta. And so we say regression, that is linear regression, because f, this true relationship, is a linear function of in the coefficients betas. Linear here means inner product, basically, or matrix product, either way. So what this assumption, so linear regression, let's just say LR, makes a simplifying assumption, namely linearity. So if we go back up to our statistical learning, we talk about how there's some space of possible f's here. And this space could be infinitely large. What linear regression does is it takes f, so here f could be infinite dimensioned. There's a whole possible space of all possible f's we can learn, right? And it's going to be really hard to figure out among that whole possible space. So the simplifying assumption is that linear regression is going to say f is basically the same thing as r p plus 1. That is, we only need to learn p plus 1 betas to determine f, or f hat, right? So the idea here is that we taken this whole, general statistical learning problem has a whole possible space of infinite dimension of possible functions. In linear regression, the simplifying model that's going to make it tractable is going to say f has a particular form here. And this particular form means that basically I only need to learn beta naught, beta 1, beta 2, up to beta p. I only need to learn p plus 1 coefficients, and then I know what my f or f hat is. And so basically it takes this kind of intractably large problem, and so let me say intractable, this infinite dimensional problem, and it reduces it down to a p plus 1 dimensional problem. We need to figure out what the betas are. So how do we do that, right? In order to determine f, we need to determine, so let me just say this, to determine f hat, we need some estimates of our betas. Let's call them beta hats. If we can get some guesses at what these betas are, then we can form an f hat. Just plug it in the formula above this one, all right? And then we have our estimate. So this is living in a world where the assumption is true. Might not be true, but if it were true, we just have to learn the betas. To learn f hat, we just have to learn the betas. So a linear regression, typically, what we do is we form a loss function where, previously we had talked about how a loss function operates on some candidate function f. But now, determining f is equivalent to determining my vector beta. So beta was my vector of coefficients. And so we can equivalently think about this loss function as a function of beta. So we're going to form our loss function. And for linear regression, right, our loss function is supposed to tell us how good f of the x's approximates y. So for linear regression, we're going to use what's called squared error loss. And one way we could write that is we're going to take our true y, and then we're going to subtract off the, let me write it like this. We're going to subtract off f of x. Say index by j goes 1 to p, beta j, x, j. So first we're going to look at the difference between the true y and the predicted y by my f, right? And we're going to square it. Why are we going to square it? Because that makes this always a positive number, and because squaring is differentiable, it's easy to work with, right? You could take the absolute value instead. We don't want positive and negative errors to cancel out, so we need something like an absolute value. Absolute value isn't differentiable, it's really hard to work with. Turns out if we use a squared error, back in the 1700s this was invented, this is a differentiable function, we are able to get a closed form solution, which was great in the 1700s when you needed to do everything by hand. We'll move on from this, but it's still the squared error, because it's so has so many nice analytical properties. It's a very popular loss to use. And so for linear regression, we choose our loss functions as the squared loss function, and then to determine f hat, we just need to determine beta hat. And we just let beta hat be the beta that minimizes our loss. So argument is the argument that minimizes L of beta. Subsequently, f hat of x, let's say x tilde or whatever, is beta hat transpose x. Is that the way I wrote it before? I wrote it the other way. I said x. I said x tilde transpose beta. Okay. So notice I'm a little sloppy here when I write things like y and x. These are just generic y and x's. Okay. So practically, to do this, our empirical loss our empirical function to minimize. Maybe I should call it our empirical risk. If our loss is a squared error loss, then the empirical risk, which we said is kind of the average. So practically what we're going to do is we're going to look at the y n minus beta naught minus the sum beta j times x n j square that. So this is our empirical risk, right? If we use a squared error, this is our empirical risk that we're actually going to minimize using this approach. All right, this is kind of the general form of it for, say, a single observation. Empirically, what we do, right, if we go back up, we average everything together. So this is our empirical risk minimization. And I guess these should be argmins, right? Argmin is the f that minimizes this. And so we do the same thing here, is we basically going to average the squared error loss over over all of our training data. So this is empirically what we minimize. This is we have our training data, our yns, our x's, and we'll minimize this. So it turns out if we let x, capital X here, we're going to call this, if we let x be our, quote, design matrix. So here our design matrix is going to take the following form. It's going to have ones down the main ones in the first column, and then our x and j, so xn1, xn2, ... xnp. So that's our first observation. Then should be n, should it be, right? So our first observation, x11, x12, x13, x1p. Second observation is x21, x22, ... x2p, all the way down to x capital N1, x capital N2, ... x capital Np. So this is our so-called design matrix. So we're just going to concatenate together our observations, which they call x1, x2, ... xn. And so capital X is our design matrix. And if we let y here, little y, be our vector is the vector of observed y's, is our vector of the thing we want to predict, then our empirical risk to minimize is, we can write it, this loss, L of beta, is the norm of y minus x beta squared, or at least it's proportional to this. So typically when we do these regression problems, we leave off the 1 over n out front, right? So it doesn't really matter if we go up to our empirical risk minimization, way up. Where is that? Up here, right? It doesn't change the minimizer to include the n or not. So typically we're going to leave it off, and in regression we typically leave it off. But our empirical risk can be written in this really nice form. So here x beta note that this takes the correct form. And so again, what we're trying to do is we try to find the beta that minimizes our empirical risk here. And it turns out, through some Calc 3 problem from hell, what you can do, because this is a differentiable function, right? So this is this norm of y minus x beta. So x beta basically gives us this. This is basically x beta over all the n's. And then we take y minus it, we take the norm, and we square it. Turns out this is actually a differentiable function in beta that we can show if you do the minimization correctly, that beta hat is x transpose x inverse x transpose times y. So this is a formula that you should commit to memory. For linear regression, this gives us beta. If I take my data, I put it in a design matrix, and if I'm minimizing the least squares error here, the beta that minimizes it, beta hat, is x transpose x inverse x transpose y. So you might remember this. This is the projection of y onto the column space of x. So the punchline of the whole lecture is that a linear regression is simply what we do is we form what's called our design matrix. We basically put our raw data in the matrix, and then we have this column of 1 out front to account for beta 0 properly. If we do that, x beta is basically the predicted values. These are basically our y hats, more or less. And so we look at the square difference between y and y hat. That's actually a differentiable function, although it's a p variable function. You could actually spend enough time taking the derivative, setting it equal to 0. What you would find is that the minimizer, basically a Calc 3 problem or a Calc 1 problem, takes this form, x transpose x inverse x transpose y. And that is almost the projection of y on the column space of x, right? If you remember what the projection matrix was, it turns out, right, so if y hat would be x times beta hat, so you can think about why that's true. Think about the math here. If x is my design matrix and I multiply by a column of betas out here, it will properly multiply through to give me the right form. And this would be the form. It would be x times x transpose x inverse x transpose y. We should really say that that is the projection onto the column space of x. So beta has kind of almost a projection. Turns out that if you want to get y hat, what you do is you multiply on the right by beta hat. That would then give you this, which is the projection. So it turns out y hat is the projection on the column space of y. So that makes sense because basically what we're trying to do when we find linear regression, we're trying to get y hat to be as close to y as possible, given that it's linear related to the x's. And so if we're constrained to work with linear combination of the x's, we're constrained to be in the column space of x. And so the y that is closest to the y hat that is closest to y but lives in the column space of x is the projection of y onto that column space. And so that's regression. So let's just summarize real quick here. This lecture what we did is we talked about the learning problem, supervised and unsupervised. And then we talked about kind of a general setup for statistical learning. Looks like we lost some text here. Let me go back and fix that. And kind of our empirical risk minimization. And our first example is linear regression. And you can write it out in vector and matrix form to make everything much nicer. Linear regression basically applies this linearity assumption to reduce the dimension of the problem to make it tractable to solve. It goes from some infinite dimensional problem down to just some p+1 dimensional problem. And the way we do it practically is we posit a squared error loss function, and we minimize it. You can write this out in vector form as the following form. As the norm, the loss of beta is the squared norm of y minus x beta. You can get then beta hat, which is x transpose x inverse x transpose y. That's just some complicated calc 3 that tells us that beta hat is related to the matrix of covariance, the design matrix, and y in that way. And that means that when I want to predict y, which I do get by multiplying my design matrix by beta hat, that y hat is just going to be the projection of y onto the column space. So let's stop there, and for this lecture, we can pick up and look at some more details on this next time.